boy here. Introduce, please, yourself. Hello, what's your name now? Yes, and yes. Where are you from? Yeah, okay. Oh, perfect. A beautiful town. Very crowded. Yes, I do not like big towns. Even Sofia is too big. And yes, what about MATLAB? Are you familiar? Yeah. O- okay. I want to tell you that most teachers from other faculties teach you how to program, while MATLAB is created not so much to be a good software developer, but to use what is available as already programmed files, which are contained in different application areas. Our application area here will be control. And perfect. Have you got the installation release so to send this to your colleagues? Yes, yes, it is. Previously, the MathWorks had some adapted release for students. Also, yes, also at the university we have a licensed release, but it is related with working in a uh, network for 20 people who use this in the network. But the network becomes very slow. That's why in our laboratories we have installed such illegal versions. Okay, if it works, you can send. Yeah, yes. The important here is that I'll teach you how to use Simulink. Simulink is a graphical language. Icons, each icon performs a given function. Um, it is created using C++, but it's not complicated. And we have there the controller, the model of the plant, uh, additional control units to see and to compare the improvements on using more sophisticated control algorithm created using Simulink blocks libraries which exist. We take a block, we move it in a new model, connect blocks, assign parameters to the functions that are performed by in each block. Then some assign some general parameters for simulation, for instance, simulation time, um, step time with respect to um, discretization in time. So the computer needs this because it operates with discrete signals. What to we put some scopes to observe results and apply generators to simulate how environment influences the control system. So everything from Simulink I will demonstrate. Then you can repeat because I will use visualization. We can record our lectures and I will record this initial introduction into Simulink, and you can download the MP4 file, the video file, and repeat everything at home and send me results. After you manage with the first self-made file, the next are ready files already created. We have only to run them and save them under your new MATLAB release, different from mine where I have created the files. So these files we have to discuss to understand. They are also given in the documents instructions for each lab, which are also in the archive for labs. So in this archive labs MATLAB, we have also the documents. So we read the manual, and there you see the copy paste of this Simulink model created, and also available in the extension of MATLAB. So in the theory you read about this, we'll discuss what is meant. What is meant is usually to compare more sophisticated algorithm with standard controller to see whether we compensate some imperfectness of our plant. The plant is a system we control. So anybody else who can introduce? The rest couldn't connect probably. Let's check once more before I start with the lectures. I want also to tell you that as a master students, we can make some self-study and like reports and present them during lectures and get a mark which will help you take the exam. So again, published in the site are the exam questions. You have 3 parts, and you can select different topics from part 1, part 2, part 3. And this topic, you can use the textbook. I will give you now all the full information. You can use my slides, prepare your own slides, read additional material. And usually lectures in the textbook are okay. And all others will listen to you presenting this material. Then I will ask them questions to understand to what extent they have understood your presentation. And I will ask their opinion about the mark. And if you have a mark from part 1, during the examination, you miss a question from part 1. If you select...
Excuse me, ma'am.
Yes.
First of all, maybe after that we can enter the exam, right?
Yes, that's right. Examination. Oh, I had to check. Is it continuous assessment or exam? Could you see Do you, do you know? I will check now. I'll tell you. I have the curriculum. It's probably again in Bulgarian. It is a selective optional subject. List one. List one. It is continuous assessment. This means when we finish with the lectures, we will finish in 5 weeks. The whole semester is 13 weeks. In 5 weeks, we'll have the lectures, and 2 more weeks, we'll have these 3 labs. And then you'll have part 2 with another teacher. So after we finish, we'll have first test for continuous assessment. So I see this continuous assessment here. List 1 is process control manufacturing automation, our subject. So during this test, I will give you different questions. You are 6, and I'll make some combination of questions, one from each part. And if you have presentation on that part, for the same 60 minutes, the time of this continuous assessment 1, you will have only 2 questions, because 1 you have already marked and you have already considered taken. So you can use also, it's not necessary, we are not limited to one part. You may decide to make presentation from each part. So from in the first 2 weeks, we'll speak about part 1. And if you decide to make a presentation, I have to know it next time. You have to prepare this presentation. I have to check it, and you'll present it in our 3rd week. This lecture I would not deliver. When we start part 2, everyone will be asked to select if they decide. If all of you want to select, the first 4 can have. The rest actually will miss this possibility, because questions should not be repeated and presentations should not deal 2 times on the same material, with the same material. So only 4 of you can distribute these 4 topics. And then I will tell you that you have 20 minutes to 30 minutes for presentation, and you may get mark or presentation from part 1, from part 2, and part 3, and finally have a mark without going to any test. Is that clear? Did you understand? Okay. So
we need to make presentation, or we will enter the exam,
yes.
or we need to make both of them.
Now, if you succeeded with the presentation and get the mark you find satisfactory, this mark will be given for part 1 in case you skip part 1 during the test. So you have option. If the mark from presentation is not good during the test, you may decide to improve and make question from the same part. The question I give you, of course, because there are 4 questions in part 1, part 2, part 3 has more. This is actually not 8, but 9. It's not 14, 15. So we have 1, 2, 3, 4, 5, 6, 7 questions. So I will make a combination of questions during the test for each of you individual combination. For instance, the first on my list will take first question from part 1, first from part 2, and first from part 3. The second in my list will take second question, second everywhere. So the third 3 everywhere, the fourth question everywhere. Then the fifth person will take first question from part 1, second question from part 2, and third and fifth question from part 3. So there is a slight repetition, but you have to answer in a different way. You cannot, you use literature, but you are restricted to use only page and a half to finish a question. So you cannot copy everything. The test is handwritten, and you send me arranged photos of these sheets, handwritten sheets. You arrange the photos in a Word document to make page after page handwritten answers to the given combination of questions. But if you have presentation and you decide to skip, for instance, part 1, you have presentation, you have decided to present this topic, then you and you have a good mark, you agree with your mark, and when the test comes the last week 8 probably, in the 8th week we have only this continuous assessment test for part 1. And you do not submit any submit answer to question from part 1. On that place, you write in your work part 1 presentation. So the mark from presentation is valid. If you have and you have the same time for answering the rest of the questions. 2 questions, one from part 2, one from part 3. You need to pass each part, so at least 3 for each question to pass the whole continuous assessment. So imagine you have mark from presentation 5, on part 2 you have 4, on part 3 you have 4. The presentation will give you a better chance, the final mark from continuous assessment 1 to be increased to 5. This is valid if you have also a good mark for labs. So good mark, I do not put mark 3, 4, 5, 6. I say good, normal, bad. The good means I can increase your final mark from the test by 1. And this can happen when we have 2 4s and 1 5, and the presentation is very important, gives you some privilege to increase your mark, and second time you have this privilege from go to work with the labs. Now I want to present myself. Sorry that I'm doing this almost at the end of our introduction. So I will write in the chat form. I'm Professor Snezhana Yordanova from Faculty of Automation. The contact is my email. You read it, you read the emails I have already sent you. So STY Teosofia BG. So you can write for contact, you can use my email and my mobile. This is the mobile for connecting with students and colleagues. So you can use it anytime you have questions. Also, you can write in the chat and initiate a conversation in Microsoft Teams. But unfortunately, I may not be able to see it, wouldn't be able to answer very quickly because I have every day a lot of classes. When I'm in class, I cannot quickly respond to the chat, but I can read my emails and the chat when I am during the break or when I finish with my classes. The mobile, if I am at the moment in class, I will answer and tell you, I'll call you later. Okay? So, about the subject. There is a textbook, Process Control, Production Automation. I told you it's a matter of how you translate manufacturing and production. They are synonyms. The textbook is in the publishing house of a university, and half of it contains part 1. Part 2 is different from what is in the textbook. So this PCPA textbook is probably 10 or 15 leva. I don't know the new prices, but I'm sure it's available. And when you decide to prepare a presentation, the presentation is sort of a report, and you need more information to make clear this topic. The slides are not enough. Then you go and buy this textbook. You can check in the library. There is English language faculty library, and because this subject started with their students, it's possible. So the authors are Neshkov first, then me, and another author. So it is light blue with interesting cover, some picture of a laboratory. So if you are going to and you are interested in control, it's good to buy it because it will be your book when you start work as a control engineer in some mechatronic systems. The laboratories have manual do not buy it because I have included PDF files. So I'll close this, and I have downloaded these labs for mechatronical systems. They are downloaded on my disk. These labs I will open, archived, and you see lab 1, lab 2, lab 3. Uh-huh. Perfect. I don't see. It's only Simulink model.
We cannot see in your screen.
What you cannot see what? I didn't see.
We cannot see the lectures in your screen.
On the screen, I shared the screen. Don't you see my screen? Do you see Labs MATLAB archive open?
No, I can't see anything. Only the list.
The list only. Yes, this is the archive. I connected my screen again. Any difference now? You see, yes, but the documents are not here. I have to upload.
I am not seeing.
You do not see only the list of students.
No, right now this is blank page. Don't have any picture or this.
So one of you sees correctly, the other doesn't. Why? You are both guests.
Şu an gözüküyor. I can see right now.
Did you manage to see?
Yeah, I quit and I enter again. After that, it's solved.
Oh, perfect. Now I will add the documents, the manuals for this. It's not here. Students PCPA. Where are the manuals? Yes, here are the manuals. So I'll use to upload material which is related with the manuals. These are, I have included, so I forgot which manuals to give you. So let's see now which are your manuals. Again, I just open to see Cascade, Smith, and Fuzzy Logic. So I need Cascade, Smith, probably this is Fuzzy Logic. Yes, fuzzy models. Because it's modern and also Cascade Smith. And this is not. And fuzzy models. So I will upload archive of this directly, because it may happen that we use it directly. They're not very big. So you have already what is contained in this tutorial. These are description of the lab. Though it's called tutorial, it's tutorial because you make some calculations, individual, and use a model to substitute the system and make. So this is the realistic system, attack, thyristor block, and so on, how we control it. And we'll discuss this, and this model is in the archive about labs. So in the you can see that predictor is a Smith model, which is read in Simulink of MATLAB. And we'll discuss, maybe it needs conversion, so I'll show you the first tutorial, the first laboratory, how to convert from one release into another already prepared models in Simulink. So here you'll find all materials you can download. And today is the first lecture, introductory, which is mine. And it's good to know next time what is your selection to prepare report. So you can look at all slides even after this lecture to have more time to make your decision, to have 1 week time to decide whether you will agree to make a presentation. I call it report, but it is actually a presentation on the topic related with one of the questions from the test. So it is contained in next lectures. So the previous one, and the first one, I start now. So I'll start recording. So hello for PCMA lecture 1 on 20th of October. So this lecture, first lecture, is introduction. We will have all 2 lectures today. Even from next time, we will reduce breaks. So hello for PCMA lecture 1 on 20th of October. So this lecture, first lecture, is introduction. We will have all 2 lectures today. Even from next time, we will reduce breaks like today to compensate the missed week as master courses started previous week. And also to compensate the lack of 2 weeks. We have reduced semester 13 weeks. So several times we'll use short break, one short break, and to compensate without additional time these missing weeks to advance with the lectures. Now the introduction is related to differentiating between different processes related with process, related with the production. Their objectives to be controlled, control configuration, strategies, the interconnection of objectives and strategies when a complete plant is to be controlled. So many processes that build the plant have to be controlled, and how the control objectives interfere. Then we'll continue with modeling of the behavior of the processes. Part 1 is half of the title of the subject, process control. Part 2 is manufacturing automation, where different production processes are studied and how they are controlled by programming programmable logic controller. We have such plants and controllers in a laboratory, and if possible, you'll have face-to-face laboratory in part 2. When we are about to finish and you have to continue with part 2, I will introduce you to our lecturer, Associate Professor Metodi Georgiev, who is responsible to teach you on part 2. Now, the processes are classified into technological. These are the processes of transformation of raw material into final products with specified properties. This is the goal of the process that takes place in an installation. This process, in order to be run correctly, is characterized by process variables, for instance, temperature, pressure. Example, if you control the microclimate in a room, you have to control temperature, humidity, drift, velocity of drift. So these are basic variables, and you need a controller in order to obtain optimal microclimate, good for to stimulate good for our to have good work, to concentrate for teaching, or to concentrate on a play on the stage. So we can have microclimate at home, at concert rooms, halls, working environment. So our productivity, our rest depends on these optimal conditions, called also comfort area. Production processes, they synchronize or coordinate the technological processes, more than one, that take place, like what I gave you as example. Technological process in a room can be related with comfort microclimate, but it can be related also as optimal utilization of light, of heating. So technological processes in a bigger sense are several when we produce the final product from the raw material. For instance, metal is first heated, then different forms are obtained, then it is cooled, then some of the forms are combined, assembled, and so on. So usually in an installation, one process takes place, but we have to synchronize the processing of this raw material through different machines or installations, and to consider transportation between machines, and also some economic and human resource issues, economic related to it, control of warehouse materials and of connection with market for selling ready product or for buying raw materials. So the production process is a bigger one, and its objective contains economic issues, not only engineering and technological requirements. Technological processes we can divide technological processes into continuous when the flows at input and output are non-interrupting, and also the information variables are measured continuously. So we have temperature between 100 and 200, for instance, for some good behavior and some good process. But in this range, we can measure any temperature, while the quality of a product is measured by several discrete values, which are usually related on measurement of measured quantities or variables. So you can measure brightness, you can measure shape, and so on. And some estimation also is included on part of the operator. But there are discrete values that characterize the quality of a product. 1, 2, 3, high is the greater. So first quality is the highest quality. Second, cheaper, and so on. Semi-continuous are processes in which we have transient modes due to change of reagents or letting in or out products. So the raw material is let in and the ready product should be let out. So they alternate. In between, there is a continuous process. Discrete is short continuous processes in comparison to operations like preparation, transportation. They are combination, continuous and discrete, different stages, and batch processes where we have a cycle. So it is continuous within a cycle, but when the cycle finishes, you let the ready product out. For instance, prepare for the next cycle, let in raw materials, combine several materials, get mixing, and so on. And the continuous cycle is again heating of this mixture so that a reaction takes place. And after that, you repeat it many, many times. So the production processes are divided depending on nomenclature and amount of production. If we have a great nomenclature, a great amount of one type of product, this is continuous, like petrol refining. Large scale, we decrease the amount, but more products are produced. The nomenclature of products is high. So still it is restricted in number, like power drives. Medium scale, still the nomenclature is like electrical appliances, shoes, greater, but the amount produced is smaller. And finally, small scale, we produce 1-2 airplanes per year. So the nomenclature of product is high, but the amount is small. Unique units are produced. So small amount of unique units, and the nomenclatures, because one of the plane is one type, the other is helicopter, and so on. So next time, different type of planes. So to control either production process or technological process, we have to meet requirements related with amount and quality of production of products, to observe environmental regulations, and safety and operational constraints. For instance, if you have installation a tank, the tank should not overflow or dry. And also, if there is a machine, there should be some safety fence, like a fence, to protect the operator not to be hurt by the machine, by the robot. If a robot is moving his arm and rotating, the reach of his arm is circulated by a fence, protective fence. Market conditions. We have also to observe the situation on the market, whether you can have raw materials, the price is changing. So the final product, economical utilization is here also of materials, energy, and capital, which is machine, premises, human labor. When we consider a control system, we have three types of control systems. The first, low level, when you have to stabilize the variable that is indicator for good production. For instance, the temperature at which we roast a bread, bake a bread. The baking requires at different stage a different temperature. So we have to observe this program of change of temperature in order not to overburn the bread or underburn inside the core of the bread. Stabilization means at a given stage we have to maintain desired temperature for a certain period of time, and this is a stabilization system. If disturbances appear, for instance, when the burner is that heats this furnace uses a different fuel, and the temperature is decreased because the fuel is not so effective, then this is a disturbance, and our control system should compensate by increasing the desired temperature that should be maintained, or intensifying the burning process with this low quality fuel. Next type is, yes?
Sorry, Professor, I lost my internet connection.
But you can read, you can have the video after we finish. You can download the video and can, so the video is on at the moment.
Okay,
can you hear me now? We'll continue.
Yes, I am
The control system is stabilization when the variable that gives us information of how the product is produced whether correctly or there are disturbances. So the stabilization control system tries to reject disturbances and maintain temperature constant. Next is the programmable logic control, where programmable logic controllers are used at full range. They have they include controllers for stabilization, but also they can control start-stop operations, transition from one operation point or one mode to another, treatment of or response to alarms, monitoring, even adaptation. You can tune your local controllers for stabilization using this programmable logic controller. So it has broader function and includes the functions of the stabilization control system. And the final, the most sophisticated, is the optimization control system. Can you hear everybody what I'm talking?
Yes.
Both of you. What happened with the other boy?
Yes, yes, I'm here.
Okay. So the optimization is an advanced technique. Usually it's related with tuning with more the previous techniques, programmable logic and stabilization. But this optimization is very much related when we control a production process. And the criteria for optimization contain some economic issues. So we have to synchronize different installations, that they work as a whole and get optimal value of a given cost function of quality, of quantity of product produced. Also, the cost function contains expenses, minimization of expenses, maximal utilization of expensive machines, and something like that. So combining engineering, technological, and economical and organizational issues. So the configurations we use for control and the control strategy, they determine which is the information variable we have to maintain, to stabilize, to optimize, or to control with respect to a given program in time schedule, and which is the variable which we have to change to obtain desired measurement of the output variable. We call output variable the one we are going to control, which gives us information whether we have a good process that creates the final product. Manipulation is the variable at the input. For instance, if we control the temperature in a room, we will use as a manipulation variable the voltage to a heater, or the flow rate of a heating agent. For instance, if we heat the room through a central heating unit, so this is the temperature of the steam in the these central heating units that are mounted in the rooms. We have also to determine how to connect. So this manipulation means we influence the output. It is input, how much we open to enter more steam, or what increased voltage will stimulate the heater to produce more heat. We determine loops connecting input manipulated variables to output and put in controller. And then we have to tune the controller. We design first the algorithm depending on the control objective. So whether we'll stabilize the measured output or we'll use try to optimize this information variable. We have already specified what we can adjust to influence the measured output. So I told you input is the manipulated, but there is also another input which doesn't depend on us and it cannot be changed by some action we undertake. These are disturbances. Some of the disturbances can be measured, and this measurement can be used for their compensation. Other disturbances are out of reach. We cannot control them. So like ambient influences. So temperature outside, when sunny weather, influences as a disturbance the temperature inside the room. And the output variables, these are which we want to control. Usually we measure them. If we cannot measure, like quality of a product, we estimate through secondary measurements related to quality, other variables. So smooth shape, good color, dimensions of the tiles used to cover different surfaces. So then we select measurements. We have to know whether we directly will measure or we'll need secondary measurements. Can we measure disturbances? And which is the device for use for measurement. So this is the transducer. It has a sensing element, some physical properties used to measure temperature. For instance, we use thermocouples, two metals. They have a hot joint between them, and the cold ends result in voltage. The cold ends should be kept at 0 degrees, so in melting ice inserted, but between the two ends there is a small voltage in millivolts when the connected part is inserted in the hot medium, which temperature we want to measure. Thus, it's physical law that creates voltage based on the temperature difference between the cold and the hot junction. So the free ends are the cold junction. The hot is the inserted in the medium, the connection between the two metals. So we have, for instance, iron copper thermocouples. So these are the two rods that are connected, and many different combinations for different measurements in different medium, and also for different ranges. Some platinum and rhodi, this is a thermocouple for very high temperature. Rhodium is not a pure metal. This is a mixture of several metals. So we have to select which variable, whether how to measure these variables, and also we select how to manipulate the input variables, those that this manipulation is closing of a valve, opening of a valve. This needs some driving component like the tap in the sink we use for water, but we manually drive it. This driving part can be a motor, electrical motor, or pneumatic actuator. The actuator is a driving part of a valve through which we supply our installation with energy or materials. So with fuel, with electric voltage or current, or with liquid, and so on. So actually the manipulated variable can be the flow rate of a liquid that fills in a tank, and we control the level to which this liquid should be filling the tank. And this is the manipulated input variable. But actually, the information variable is related with the voltage used to drive to the electrical motor that drives the plug to this valve. So a valve, it is a disconnection of the pipes through which we have the flow of energy related or material related matter. So this pipe is disconnected where the valve is mounted. The valve is a restriction which is variable. Imagine that there is a plug that is driven up and down, and when down, it closes the material through the pipe, and when it's up, it's totally open and has the same diameter as the original pipe. So the valve has restriction to the inflow of material or energy, and this restriction is controlled by opening more, so moving the plug up, or closing more, moving the plug down. So displacement of this plug vertically is related to change of the flow rate of the material that supplies the installation and allows the process to be controlled. So to reach desired level, desired temperature, what we actually control the output of the so-called plant. So the process inside the installation is characterized by this input voltage to the actuator and output variable that gives us information how well this process takes place inside the installation. The information variables are important to judge whether we'll have a product with desired quantity and quality, finally. So usually the actuator can be controlled by current, by voltage, if it is electrical motor, by frequency. Also, if it is a pneumatic actuator, by pressure of air. If it is hydraulic, by pressure of a special liquid. And pressure or voltage or current is the output of a controller. So, and the input of the controller, it has two inputs. One is reference, desired value, and the other is measured output. So we compare measured output with desired value we want for level, for temperature, and the error is processed under a given algorithm. So we have to know where to put our controls, how to connect variables that will influence the control variables, and we can change them through control action. So pressure, voltage, and so on is the control action. And then we have to know the algorithm and the parameters of this algorithm. It's the final step in this design of a stabilization control system. So the example is a constantly stirred tank heater. It will be present in many other topics as example. So we have a tank, we fill it with liquid. The inflow is characterized by flow rate. This is the quantity of liquid per unit of time. And the initial temperature. So there is another installation before this tank, and this installation produces liquid with a given flow rate and temperature. These are the initial temperature of the fluid. In the tank, we have to control the level and the temperature. To control the temperature, we need this serpentine, a piping system through which we pass hot steam. The flow rate of the steam is controlled through this valve and actuator. As I told you, the opening in the valve is greater or smaller depending on whether this motor moves the plugging element more for closing or opens moving it in the other direction. So we control the flow rate through the voltage to this actuator, which is the output of a controller. So how we control this level? This level we control when we measure the level, compare with desired level. The difference called system error is input to a controller, and depending on the error and its sign, the controller opens more or closes more the outflow, preserving more liquid inside. Or, second variant, this valve is mounted at the input. The inflow is increased or decreased through the control action of the controller that says to the motor to move the plug for closing down or lift it up for opening of the valve and more fluid entering. So if the error shows the level is beneath the set point, this variant here means we have to increase the level. That means we have to decrease this opening, less liquid to leave the tank. But if we have this variant of application of control action, for small level, we need more inflow. So the control action should open more this valve, so to let more liquid inside the tank. So we have a process which is related with the stabilization of two variables, temperature and level. And we have manipulation of the heating agent to influence the output variable temperature, and manipulation of flow rate at the inflow and outflow to manipulate the level. So the control objective, stabilization of volume, because the area is constant, cross-sectional area of tank is known. This volume is related directly with level, and stabilization of temperature. What we are going to select for manipulated variables. These are variables which we are going to change flow rate of heating agent, or we can manipulate flow rate of living liquid and input liquid for maintaining desired level or volume. If we select the proper two manipulated variables to influence the two outputs so that they keep constant values despite any disturbances, then the rest can be considered disturbances. What we have? Disturbance, if we use this for level control, then initial flow rate will be the disturbance on level. Initial temperature will be disturbance on temperature. But these two variables and their manipulated control actions are related. Why? Because if the level is reduced due to this flow rate disturbance at the input, temperature will be increased for the same heat because less liquid is going to be heated and the stir makes temperature evenly distributed throughout the whole tank. So what we have here, this disturbance which changes level, or the control if we decrease level by deliberately changing the desired or set point level, this reflects into increase of temperature. If opposite, we change temperature by changing either the set point for temperature. So set point is desired value, which has to be maintained, so the stabilization. It's called also a reference. So we measure through thermocouple temperature, compare with set point. The area of the controller is the input to the controller, and the controller tries to change the heating agent in a way to compensate this area, to reduce it to zero, so measured temperature will be exactly the desired temperature given by this reference. So if we change the set point, so we have to increase temperature, for instance, then some of the liquid may get evaporated, so the level will be reduced. So there is interconnection between these two variables. We can separately control temperature using a closed loop. This means our control action on the valve is aiming to change the temperature, the output of our plant. So plant is relating output information variable with the input manipulated variable or the controller output. So we do not measure flow rate, but we know the output of the controller, the voltage to this valve. So our plant has output the end of the thermocouple because we cannot know the temperature unless we measure it, and input the output of the controller. So the voltage, the current, or the pressure of air or liquid, which will make this actuator change the opening in the valve and respectively the flow rate of heating agent, or in here of liquid. So changing the raw materials, the energy needed for the process inside the tank. And the process is characterized by these two information variables, so we have interconnection between two plants or multi-variable plant. This means several variables that are controlled in this process by several manipulating variables at the input, which are interconnected. Each input influences both two or both outputs, level and temperature. So if we have only to stabilize temperature, we use this closed loop. Why close? Because the input to the plant influences its output. So through the controller. Here we have closed loop system or feedback control system for level in two different variants. So the first is the application of the input at this point. So we change the flow rate at the output. This way we influence level. So it is again a loop, closed loop or feedback system for level. In the other variant, we have different control action. It should react to the magnitude and the sign of this error in a different way. To increase measured level, we have to decrease the opening that lets liquid out. But for the same increase of level, if we use this variant, we have to increase the opening, not to decrease, but to increase. So different control action to have the same effect on level. So if input and output are connected through this way, we have a feedback or system, closed loop system. We can have also open loop system. Here we demonstrate how we measure temperature or disturbance of the inflow. This temperature, because this disturbance we can measure, we have another type of controller, compensator, which influences the heating agent that changes inside liquid temperature. So it doesn't change this temperature, but another temperature. So we have open loop controller. The controller is called compensator, and its aim is to influence this opening and supply with heating agent before the new temperature of the inflow has impact on the same temperature. So the inside temperature, we know that after some time it will influence this initial temperature of the fluid, of the liquid, will influence the inside temperature. If we have cooler inflow, for the same steam and heat, the temperature inside will be decreased. So, measuring the disturbance, we act with advanced compensation. Before this liquid with cold temperature enters, we have already increased the heating agent, so inside temperature will not be influenced by this disturbance. But this is called feed-forward advanced compensator in open loop of disturbance. So there are many measurable disturbances, all which we cannot measure will be felt in this temperature, and the closed loop system combined with this one is a good example how to compensate the main disturbance through feed-forward compensation, and the rest of the disturbances as well as change of set point will be controlled by closed loop system, because each disturbance will influence this temperature and this controller will start operation. So the overlaying of these two principles is a combined principle, combining feedback in a closed loop with feed-forward compensation of disturbance. If we have several outputs that characterize a process and several manipulated, one manipulated for each output, and the manipulation of X1 influences all outputs. We have a MIMO, multiple input, multiple output system, and the controller is MIMO controller or multivariable controller. We can have a feedback system if we measure all variables, like in previous example, temperature and level, and synchronize the change of manipulated variables so that we change only one of these variables at the output, only y1, because the change of x1 will influence the rest. We have also to change x2, x3, and xn to compensate this interconnection. But inferential is the control when we want to control unmeasurable variables. Then we measure what is measurable, use estimator, and obtain estimated unmeasured controlled variable. And the controller tries to stabilize these unmeasured but estimated controlled outputs we want to control. We want to stabilize, or they should follow a desired schedule in time, or should follow changes of some oscillatory or different variable. So apply different principles for operation of this control system. We can also measure several disturbances and coordinate the manipulation variables so that these disturbances do not influence the outputs. They influence the plant, but this controller is fast operating and reduces this impact of disturbances on plant output. This is feed-forward MIMO control because this compensator will have several inputs and control actions to coordinate the compensation of disturbances when we have a MIMO plant. This is a process for which we have information variables at the output and manipulation variables, which is also information, so we measure them somehow, and the connection between input, output, and the differentiation, what part of the input can be manipulated, can be changed by a controller or by operator manually, and what other inputs we cannot change, but some can measure, some cannot measure, ambient influences, for instance. So these are the disturbances. So the inputs are two types. The ones we select to manipulate, and we can manipulate, and others which either we measure or we cannot measure. If we measure, we can use for compensation. These are disturbances. So what we want is to stabilize, despite the disturbances, to stabilize the output of our process. So if we have a complicated plant, after that we'll make a small break and continue to 6 o'clock, no more. So what we have here is two installations which are connected, so that the final goal is to separate. Let's explain each installation. So the first is jacketed, constantly stirred tank reactor, which means a chemical reaction takes place between these two reagents. A that feeds this reactor with flow rate Fa and initial temperature Ta. The next has again feeding flow rate or initial flow rate and temperature. They are mixed inside. Steam maintains desired temperature. The steam gives its heat to the inside components and is turned into condensate on leaving a sort of serpentine or jacket because the steam is vapor, and here it is called steam, and that's why condensate. So a reaction takes place, but not the new product is C, but part of A and B are also present in the output, which is pumped. So we have to separate reagents A and B from final product C, which is expensive, and how we separate. We separate in distillation column. The idea of separation is the different point of evaporation of A, B, and C. So this distillation column has vertical distribution of pressure and temperature. At these are valves like plates. The feeding is selected where the temperature keeps A and B in gaseous state, but the product C becomes liquid and drops down. So, but by dropping down, some of the vapors are taken by the drops and go down. These A and B vapors, they go up, but with the velocity they go up, the energy at this temperature, they may take some of C up. So there are two boundaries to force. The first one near the bottom is related with the reboiling of this bottom product, which contains some vapors. This bottom product is returned by reflux after being additionally heated. So we increase the temperature here to make a boundary. All A and B, which are taken by the drops of C that reach this boundary here, where the temperature is again increased, they get energy to be separated from the drops of C. So only drops of C and a little A and B will appear in the bottom product. So the purity depends on this boundary and upper boundary. So the upper boundary is the top product, gaseous, is condensed and separated in these two additional installations. The condenser is cooling these vapors to obtain liquid A and B. And this liquid A and B, part of it is returned to make the upper boundary, to cool this part in case some C is taken by the energy of the gas. The gas should contain mainly A and B, but some C liquid has energy, and here it's cooled and additionally cooled and dropped. And only gas of A plus B should be present on the up product, which is called distillate. So distillation column separates two components, and because here we have A and B at cold temperature, it is returned to first installation, together with the new A and B products. So we cannot keep desired fixed ratio. So the flow rate A and B should make a ratio which will ensure less A and B in the product. So not to have much of the components, but to have the final product. So they all should react to result only in product C. But unfortunately, we do not know how much A and B will be added. So the ratio flow rate of A over flow rate of B is violated. So the objective to keep maximal flow rate of C at the bottom with high purity highly depend on the conversion rate of A and B in this jacketed constantly stirred tank reactor. So the idea is to preserve this constant ratio and constant temperature, but however the impurity, which is not constant, is different and violates both this distillate that is returned is at low temperature. It also is impact on the desired constant temperature. So this mixture and reaction cannot keep constant temperature due to this reflux. So the two objectives to keep constant ratio, to have less A and B in the final product, which is the mixture of result of reaction C and initial reagents which could not react because the ratio is violated. So this leads to the other objective, to keep pure C product in the bottom and maximal flow rate of the product C. So you see how the installations put restrictions on the objectives of the next installation and how the next installation influences the objective of the first installation, in which is the conversion of A and B into C to be maximal. So this is how you as a control engineer have to decide which are the objectives and how to reach them, how to set new restrictions on previous installations, and so on. So we have also operational constraints not to overflow or get dry this distillation column, and of the constantly stirred tank reactor, and how to consider different disturbances as a distribution of pressure along the length, along the height of the column, temperature of the coolant, temperature of the steam, and flow rates here and here. So flow rates, if you control flow rate, here these input flow rates are related with previous installations that produce A and B and heat them at temperature TA and TB. So you see there is a constant revision of the objectives. These objectives, how to influence the objectives of the previous installations, and they how to put restrictions on the flow rates of the previous installation that produces A and B. So there is interconnections between specifications, control objectives, operational constraints, and disturbances. So next is topic I'll start with modeling of static and dynamic behavior. And please look at the next lecture and the other lectures, of course, to select a proper presentation and tell me next time. So, what about 5 minutes break? We'll have another 15 minutes after the break and we'll finish. Is it good for you to rest for 5
Okay,
minutes?
Professor.
Okay, that means
okay for
10 minutes to 6. We'll continue for 15 minutes to finish the topic of modeling. Okay?
Okay.
By now, I'll stop the recording and you'll have 2 videos.
Okay.
So second half of this lecture, 20th of October. This lecture is devoted to how we acquire knowledge about what we are going to control. We need a model of our process that connects input and output variables, those information variables. This is necessary, for instance, this is what we are doing every time with every new thing. We try to learn more about this. For instance, if there is a car, we have to push. We will try to see what force to apply. Is it possible that we do this ourselves, or we need a second person to help? Or if we push it and the car is very light, it will go very far from us. Or if it's very heavy, it wouldn't move. So we make some tests to understand how heavy this car is, how it's moving, how the road is, and the connection, the friction between tires and road. to move it to a certain place. What happened? So we try to learn by modeling what this process is, whether it needs a very rough and big control action input to reach the desired output. So whether it with mild input, we can move the output to the desired value. So this is the modeling. And our process is function of time also. So output may change with time, or it may not change with time or depend only on input. So eliminating time, we model the static behavior, considering the time. For instance, we push a car and it starts moving, accelerating, and we are interested on the road when it will reach a constant value of velocity. So this will be the steady state, but it will be reached gradually. We make transition from one steady state, the car doesn't move, to another steady state, it moves with some small constant velocity. So we study what force to apply to reach this new steady state. So we need to know its model in modeling of dynamic behavior. The models usually, so the processes are described by these information variables, which gives us idea how good production will appear in this process. But also we can have information because we can measure these variables at the input and output can be of different physical nature, electrical, thermal, hydraulic, like pressure of liquid, temperature, voltage. The modeling usually is based on either experiments or derivation of some conservation laws for energy, matter, and momentum. We model a system which contains elements. Elements are structural units that accumulate, transform, transmit, or disseminate either energy or material or momentum, motion. The element allows to be determined by measurements in 2 points in space, the beginning and the end of the element. And we have connection of several elements. So finally, in a system, according to the conservation law, for instance, for energy, the energy that is created is formed as a sum between energy transformed and we add the lost energy. So the created energy is the result of this sum. This means we have a closed system in a volume. The model also is related with the variables we measure at the input output, which can be measured in 1 point. They are called quantitative variables. Quantity of volume, entropy are such variables. Flow rate, they are variables that pass through element. They are like current. flow rates, fluids. Potential difference is a cross variable. We measure it in 2 points. And usually 1 point is the reference ambient or zero temperature, absolute zero temperature. Pressure is measured through this way because the measured pressure is compared to absolute pressure or to vacuum. So velocity, voltage also are measured in 2 points. So besides variables, the model contains parameters which usually are defined by the variables. For instance, there are resistive parameters. These are like resistance in an electric circuit. This is the variable potential difference over the flow variable, flow rate. Potential difference is voltage. Flow variable is current. If we consider changes, it will be the derivative of P variable with respect to changes of F variable, flow variable. Capacitive parameters are analogous to capacitance in electric circuits. They are formed by the ratio Q variable, quantitative variable, over a potential variable for potential difference. And we have also inductive components, inductive parameters. They are constants, but they give us are related with inertia, with capacitance, and these different physical nature systems have analog variables, quantitative, flow, and potential. For instance, for electric scheme or for electrical system, we have electrical charge for quantitative, while in pneumatic system, the corresponding analogs are weight, volume, entropy. For flow, current is in electrical system, but it is flow rate for the rest, or speed of change of entropy in thermal system, mechanical force, rotational momentum in mechanical rotational system. So we see that if we have to obtain model of a mechanical system, we can make this physical analogy model. So we can turn this mechanical system into pneumatic, considering the analogy between variables, which are quantitative or flow or potential, and analogy between elements. Most often, or the general analog based on analog of signals and elements, components, we usually use electrical circuit. So each of these systems is easily transformed into electrical model, which to substitute the system in order to perform experiments which are safe and will lead to new knowledge about the initial system. Electrical circuits are the general model of all other physical types of systems. This is due to the great variety of elements with different ranges, resistors, capacitors, inductance, potentiometers, and so on, which are analogs for the other system elements and variables. These analog elements and variables allow us to carry out a variety experiments which are easy to repeat, full control over the experiments. They are fast, and also these fast experiments can use variety of changes of signals and parameters to see how the mechanical system behaves. Mechanical system, okay, but imagine it's a thermal system. The thermal systems, they are related with heating, cooling, which are very slow, and each experiment can be dangerous. We cannot change parameters and elements in great range. Thermal system, it needs a heating element. It is serpentine with a given surface. We have to reconstruct a new thermal system to see how the different surfaces and the different parameters of the heating agent influence the heating process. While when it is transformed into electrical model, this is easy to do and cheap, and the experiments are safe and cheap, fast. So we can change electrical voltage that feeds the electric circuit in a great range. In this way, the corresponding thermal flow, so the voltage is potential difference, the temperature difference will change, or the temperature inside this thermal system. We can get new knowledge very fast, but we have to be sure that this electrical circuit precisely models the process in the thermal system. But the most important thing in this transformation, due to the isomorphism between systems of different physical nature, this means the possibility to use analogous variables and elements to transform, to build a model of a more complicated system, and the model finally to be electrical. Why? Not only because of all these advantages I mentioned, but also because in electric circuit we know the basic Kirchhoff's law for the nodes and for the loops to compute the model, to obtain a model, analytical, mathematical model based on this conversion of real system into electrical model. The electrical model is solved to obtain equations. So finally, our model will contain a number of equations that connect the independent with the dependent variables. Independent are those we control, those that come from environment, from outside the system which we are going to model. So for the constantly stirred tank heater, external is the heat that comes from environment with the steam. External is also the cooling effect of environment. If it's open tank from above or from the walls of the tank. This table showed us how to obtain a simple system, electrical, as a model of a more complicated, and from it to derive the mathematical model using the basic laws which are derived for electrical circuits. Now I'll give you another way to derive the mathematical model. We need mathematical model, and we can solve it to study how input influences output. So we are interested in dependent quantity, mainly output, as function of the independent quantity, external influence like input. This can be derived based on the conservation law. For our case, mass balance equation, energy balance equation, and balance of forces in preserving momentum, momentum balance equation. Here, we use two types of balance equations because they are related with our example of constantly stirred tank heater. The heating of a liquid, the important was to maintain desired temperature inside and desired level. The level is bounded with the flow rates as input, so we use volume with this level multiplied by the density of the fluid. The change of mass inside the tank is related with this balance equation. If we have inflow, mass per unit of time is the flow rate. F is the volumetric flow rate multiplied by rho becomes the mass per unit of time that enters the tank, and this is the mass per unit of time that leaves the tank. And here we have mass produced inside if we have some chemical reaction, or the mass consumed inside. In our constantly stirred tank reactor, we do not have creation or consumption. This mass balance equation in chemical reaction can be distributed to all components in the reaction. The energy balance equation is related with a change of energy due to change in internal energy, so temperature, or kinetic energy, movement, or potential energy position. So in our case, energy is related only with temperature because we do not have in the tank movement or some position which may turn potential into kinetic energy. Neither we have work performed. So this balance equation is related with the heat that comes with the inflow, this mass of inflow, with the leaving liquid minus the heat that leaves with the leaving liquid, the external input or loss through ambient influence. For instance, ambient temperature is very low and we lose energy. So this is the relationship with environment. We introduce heat through serpentine and hot steam, or we lose heat because ambient temperature is very low and influences the process. And this is the shaft work. Either it heats, adds energy, or takes energy. So it is the energy is consumed to rotate some wheels, for instance. So this is the energy balance equation. In case of constantly stirred tank reactor, no kinetic, no potential, only the disbalance of flow, and this additional heating from serpentine makes the equation. This equation can relate temperature with heating agent, while the first equation relates level with flow rate at inflow or at the outflow, the disbalance of these flows actually gives us accumulation of liquid and influence on level in the tank. So the mass in the tank, the energy changes due to changes of temperature, so changes of kinetic and potential energy is zero. The change of this total energy depends on the change of internal energy, which depends on the enthalpy where we see the presence of temperature. It's measured through temperature of liquid. So this is density, volume, heat capacity of the fluid, and the reference temperature known. This is the temperature for which the specific enthalpy is equal to 0. So according to the mass balance equation, we have flow rates. This is mass per unit of time. The accumulation, so the accumulation of mass, A and rho are constants. Only T changes with time when there is a balance between the mass that enters and that leaves. And when these two masses are equal, no more derivative is present. So H stops changing with time and the derivative will become 0. Then we'll have the steady state model. But dynamic model, as you can see, is more general. This is from it we can obtain the static model when derivatives are turned into 0. So rho is cancelled. So the simplified differential equation of first order is relating input with output. And the energy balance equation that relates enthalpy with inflow and with minus enthalpy heat leaving with a living fluid. Any extra from environment heating, we differentiate the accumulation of energy. This is the enthalpy. So the disbalance between heating and entering heat and leaving heat and additional heat. We have here two variables that change with time in this derivative, H and T, temperature, so level and temperature, the two outputs of our plant depend on time. Here the others are kept constant except the control output, the output of the controller. This is the quantity of heat and one of the flow rates. The other is disturbance, for instance, or kept constant. It can be constant because the living liquid depends on the hydrostatic pressure, so it changes with level, while the other is controlled, for instance, by the controller. So actually, from these two equations, after substitution of the first into the second and differentiation, the derivative of two variables. So we have A and T are the two variables. And this derivative is the derivative of product of variables. So what we have here, this complex derivative of this product, the rest are constants, are not included in the derivatives. So the derivative of temperature multiplied by h and the derivative of h multiplied by t, and part of this derivative a dh dt is substituted by flow rates. Finally, we'll obtain the two first order differential equations, the first with respect to level, the second combines level, but the derivative is with respect to temperature. And this is the dynamic model obtained through conservation laws. Conservation laws are used usually in combination with experiments. This model connects output variables with input variables that will control or change these output variables to keep a value equal to desired value despite disturbances, for instance. So in this case, the dynamic model can be turned into, so let's go again to where the model is turned into steady state model after some time when we have balance of input and output mass, then the level will reach another position and will stop changing any longer. The same is with temperature, so these derivatives will be zero, and the steady state is the steady state model contains only algebraic equations. So they are complicated, and we can obtain on their basis the steady state characteristics. Usually in plants which we control have nonlinear steady state characteristic. Some of the input variables, usually the disturbances, one is kept constant, the other takes constant values to make a family of steady state characteristic. And here opposite the Ti is kept constant, and we make a family of steady characteristic for constant several different values for the flow rate at the input. The steady state input and the steady state output make the steady state characteristic for fixed other input variables, disturbances, and the gain with which the change of input reflects on change of the output. This is the gain. So any change of input, so the change of output per unit change of input gives us approximation of the gain. For small changes, we have derivatives, and these derivatives is the tangent of this tangential line and abscissa. The tangent of angle alpha gives us the gain. This tangential line in different operation point is defined by the input-output couple. So for Q0, we have TS0 and TI0, so all inputs should be defined. And this is one operation point. Any point from the steady state characteristic can be used for operation. This is the main point in which a given plant operates. So in another operation point, the tangential line will constitute different angles, so we'll have different gain. The gain of the plant, this is important value because it shows how unit change of input influences the output. For instance, if we change Q, which is the heat, for instance, calories by 10, and in this operating point, this causes increase of temperature by 20. The gain is 2. But in another operation point, the same change 10 may increase temperature to 50. So we'll have gain K. So one and the same change of input causes 2.5 times greater change of temperature. The sensitivity to the same input is increased, which means now a controller will give these changes of input. So we'll know if we want to obtain fast and big increase of temperature, we have to work in the second operating point. So usually the change of a gain in different operation points shows that our plant model and behavior are nonlinear. So the plant is nonlinear when its model parameters change in different operating points. Industrial plants, as a rule, are nonlinear. They are difficult to control. We usually control them by fixing a narrow area around a given operating point. At this operating point is our reference. That means we want to have a temperature equal to 120 degrees. That means the set point is fixed into the operating point, somewhere where we have a big linear range. This curve can be approximated by the tangential line in some area. So around this reference, the reference means that our final temperature will reach this reference. This is the aim of the controller, to maintain the temperature to a desired reference. So we select the reference where the linear area around it, so the line, tangential line in the operating point, is very close to the curve, and this area to be big enough. So then we use linear controllers and methods to control system. We consider it linearized, and methods to control a linear system are much easier. Most of the time we'll control linear systems. Only the last 2 lectures will be devoted to nonlinear plants that are controlled by fuzzy logic or neural networks which are nonlinear controllers. So nonlinear plants need more complicated, non-standard, usually nonlinear controllers. So I will stop here because it's too long. From experimental approach and the next lectures which are related with the test, the 4 questions from part 2. So I want that one of the lectures is yours or your colleagues. Just select different lectures. You will read them, read in the textbook, and show how on the basis of this selected topic given in my lectures, in my slides, you can solve a problem from the test from part 1. Okay? So I finish.
Are you hearing? Do you hear me?
Okay, I finished the record.